Hello everyone, I'm humanHardDrive, and today on Electronics 101 we're going to be talking about filters, specifically passive filters. This is a video suggestion I've received from a couple people, and I thought, since I'm coming back, I thought this would be a great one to start with. So, what is a filter? It's a good question to start with, address the topic. What is a filter? A filter is a series of components designed to reduce the amplitude or attenuate of an unwanted frequency in respect to some cutoff frequency that we'll talk about a little later. Now, in the world of filters, there are two categories, one being passive, what we're going to talk about today, and another being active. The main difference being that passive relies solely on passive electronics components that don't require an active supply of power to function. Whereas active components require that power and in some way amplify and shape and use power to amplify and shape the signal. So today we're going to be talking solely about passive filters, and we're going to be talking about RC filters, resistor capacitor filters. Now, there are three subtypes of both passive and active filters. We're going to talk about each one. Now, the first one being the low-pass filter. Now, I talked about FC. FC is that cutoff frequency. Low pass reduces the amplitude of frequencies greater than FC. So it passes F's less than FC. See, it's a low pass. And in terms of the ideal filter, if we were to look at, say, a graph of amplitude and frequency, it would look something like this. And this point right here is F sub C. And this is all that it would pass. So that's a low-pass filter. The next kind is a high-pass filter. So I'm sure you can guess what that does. It passes frequencies greater than FC. So if we were to look at a graph of that, amplitude, frequency, it would look something like this. And this it would pass. And then the final type of filter we're going to talk about is something called the band pass filter. And what that does is it reduces the amplitude of frequencies greater than and less than FC within a certain bandwidth, hence the band. So it passes F's minus, there's a notation for this, let's see, FC minus band. I'm using that as shorthand for bandwidth, less than FC plus the bandwidth. And so if we were to look at a graph again, it would look something like that. This is what it passes. So here we have F plus band, or minus, gonna see if I can undo that. F minus band, F plus band. Okay, now, from here on out, it's going to get very mathy, and this could be quite a long video, so I'm just warning you now, this is going to get a little head-hurty. So let's talk about low pass first. It looks something like this. It's got a resistor, and then it's got a capacitor attached to it. And here's the input. Here's where the output is. Here's C, and here's R. And in this case, order matters. Note that the resistor is first, then the capacitor. Now we're going to talk about a little bit of math. We know Okay, it's got a resistor, and we also know that a capacitor acts like a resistor. It has some resistance as it charges. And the reason this is important is because it changes the behavior of the way the device functions. So we know that when you've got two resistive components in series, you get a voltage divider. Remember this equation, Vout equals R2 over R1 plus R2 times Vn. That was the voltage division equation we derived for resistors. And there is something similar to that used to get the voltage out from a filter. The capacitor has this quality to it. It's called reactivity. And it goes something like this. Xc, that's reactivity of a capacitor, is equivalent to 1 over 2 pi Fc. That's wrong. That's not supposed to look like Fc. Fr. No, it is Fc. Sorry. Fc, because I don't want it to look like the Fc is in the cutoff frequency. What this does is it tells you, this gives you a measurement in ohms. That tells you the resistance a capacitor is going to have in reference to how much frequency you're putting into it. So if we were to, say, construct something with a capacitor of, say, 1 microfarad, that's 10 to the negative 6th farad, and we were to put in a frequency of 1,000 hertz, we would probably get, we would get something in the range of 159.155 ohms. That's how resistant it is to the frequency. So that's the resistance of the capacitor. Now, the thing that's going to get a little tricky is here, there's a summation thing. That summation has to do with something called impedance, which is resistance to change in current in an AC circuit as it results with voltage. Now, a resistor's impedance is its resistance. It doesn't change with voltage. However, the more voltage you put into a capacitor, the more resistance. So that's going to change. It has an impedance, and that has something to do with its reactivity. Its summation, the summation down here, looks like this: R squared plus X sub C squared. So if we were to take all of these and put them together, we get this equation out. Vn times X sub C over Z, which you know is equal to X sub C over the square root of R squared plus X sub C squared. So if we were, and this is solely for low-pass filters, let's just keep that in mind. So if we were to have a sine wave oscillating at, say, well, I won't deal with that, peak to peak of, say, 5 volts. So that's going to result in a Vn of 5 volts. We'll use the same capacitor, 10 to the negative 6th farad, that's 1 microfarad, and we'll put in, say, I don't know, 100 ohm resistor. R is 100 ohms. At 10 hertz, okay, Vout is equivalent to 4.9999 volts. So it's pretty close. At 100 hertz, or 1,000 hertz rather, Vout is equivalent to 4.233 volts. So it is a change. It's not that dramatic, and we'll talk about why it's not as dramatic in a little while. But if we were to look at the gain, we all know the gain equation. Gain is Vout over Vin. So the gain for this is, well, let's just say it's 1. It's pretty darn close. The gain for this is something less than 1. I didn't actually do the math out, and I apologize for that. It's less than 1. The gain is less than 1, meaning Gain of 1 means that the input voltage is exactly the same as the output voltage. Gain of less than 1 means you're getting less out than you put in. So it's successfully reduced the amplitude of higher frequencies. So thus demonstrating the effect of a low-pass filter. Now, if we were to take that and plot a curve, here's frequency, here's amplitude, and it's going to look a little better than the other curve I drew. This is terrible. I apologize. Let me try and draw this a little bit better. There we go. Here's amplitude, here's frequency. It's going to look something sort of like that. And I'll put in some dotted lines so that you can see what the heck is going on. Okay. So this is for a low-pass filter. Okay. And one of the first things you should notice is FC occurs after the amplitude has started to dip. Okay. This area here is called the roll off. And f of c occurs a little while after it started to roll off. And it occurs at a very specific point, which we'll talk about in just a little while. Now, this slope here, which I haven't depicted very well, is a constant slope. And in the case of this filter, it's negative 20 dB per decade. Remember, that's dB is decibels. I should probably give you this equation too. Gain, in terms of decibels, is equivalent to 20 log, that's base 10, of V in, or no, not V in, V out over V in. Draw that 10 a little better. There we go. So this is, we'll talk about that in a little while. So that's what that looks like. So, and constant slope. Okay. Now, you can tweak how where that FC is in relation to this roll-off and at what level, which we're going to talk about in just a little bit, and the slope of this line. Again, this is a constant slope. I didn't draw it very well. The filter I drew for you a couple pages back, where was it? There it is, this, is something called a first order filter. If you add increasing orders to the filters, you change the effect. So if I were to draw, say, a second order filter, all it is you take, there we go, a first order filter, and you add another filter on the back. And that's it. This is now a second order filter because it has two filters in it that both accomplish the same thing. R1, C1, R2, C2. Now, so that's a second order filter. And that changes some of the behaviors. First of which being, changes the equation to determine cutoff frequency. Now, I'd mentioned a couple pages back, or maybe not that many pages, right here, about this difference in voltage. It's because of where each of these frequencies lie in relation to the cutoff frequency. Now, here's the formula to calculate cutoff frequency. For a first order filter, it's FC equals 1 over 2 pi RC. Again, this is first order. For a second order filter, it's more like this. Second order. Okay. So you do the math out and you find that the cutoff frequency that I used here, given the resistors and capacitors we put in, gives a cutoff frequency of 1591 hertz. So that's closer to the 1000 than it is to the 10. So the 10 has a greater gain than the 1000 hertz. And if we were to get even closer to 1591 hertz, you would see even less and less in voltage until eventually you got so far that there is no voltage left anymore. Okay. So, let's talk about some more behaviors that change. Now, the slope. This is, remember, because this is a low-pass filter, as frequency increases, you get a negative slope. It's dropping off. So, it looks like the slope you get is actually just negative 20 N dB per decade, where N is the number of filters. So that changes the slope. Now, I'd also mentioned a while ago this point here. This occurs after the roll-off, and just at the start of this constant slope. There is a way to find out what that point is. It occurs at a specific gain, and that gain is given by, this is in decibels, that gain is given by, I'm going to give it to you not in decibels. You know how to convert it to decibels. You just put it into that equation. You just put it into this equation. Oh, there it is. This equation up here. You're just going to plug it in for V out over V in. The gain at FC that the constant slope begins at is given by 1 over the square root of 2 to the n. Remember, n is the number of filters. So, with one filter, it works out to, I think, when n equals 1, it works out to 0.6, roughly. And when n equals 2, it works out to 0.5. So what's happening is it's going to start... Oh, wait, before I talk about that, I'm going to show you one more thing that changes. It's also going to start moving back. That frequency at that gain is equivalent to the cutoff frequency you calculate times the square root of 2 to the 1 over n minus 1. So at one stage with just one filter, 2 to the 1 minus 1 is 1, square root of 1 is 1 times FC. So the frequency at that gain is the cutoff frequency. But as you add more and more filters, it's actually going to start pushing back. It's going to start pushing back. It's going to start getting more and more up that roll-off curve, and eventually at infinity there won't be a roll-off curve, and there will just be a slope of negative infinity. It will at an infinite number of filters, you will get, and I gotta go way back up for this, you will get the ideal low-pass filter. Okay, so that's it for low-pass filters. I know this was, oh wait, sorry, one more thing I gotta talk about before we move on. Because filters employ resistor-capacitor circuits, there is lag, and that lag is called phase shift, denoted by that character. Sorry if I don't know the Greek name for it. For a low-pass filter, that is given by negative A tan, that's arctangent, or the inverse tangent function, 2 pi f r c. Now, phase shift, it looks something like this. If I were to draw a line, so here is your input wave, phase shift does something like this. If I can choose a different color. There we go. Phase shift does something like this. Okay, that's pretty good. It causes a little bit of an offset called the phase shift, and that is given in either degrees or radians, depending on how you set your calculator. So that's the phase shift. Okay, so yes, that was a lot of math, and I'm sorry, but it makes the rest of it go a lot easier, because I've already defined a lot of terms, and it just starts making a lot more sense. Okay. High-pass filters. Now remember, order matters. I told you that in the circuit. Yep. Drawing that backwards. Going on about order matters, and I can't get the order right. In this case, it's going to be capacitor first, resistor to ground. And then there's the output. Input. C, R. Okay. Now, the formula to calculate the voltage you get out versus in is different than the one for low pass. Remember, that was all the impedance thing. It's different for this. It actually works out to V in out over V in is equivalent to R over R minus the reactivity of the capacitor. So you can solve that out, and you get V out equals V in times R over R minus X sub C. So that's the voltage out. And if we were to draw that curve again, there we go. Amplitude, frequency. You get a curve that looks like this. And it follows almost the exact same behavior that the low-pass filter does. Here's your FC, and it again occurs at the in this case at the end, if you're moving from left to right, at the end of the constant slope. In this case, the constant slope is exactly the same, just with a different sign. In this case, it's 20 dB per decade. I'm just going to abbreviate that DEC. And so it looks like that. Phase shift in this case, phase shift equals arctan, or atan, of 1 over 2 pi f r. Oh, no, there's no f in this case. Sorry. RC. And okay, and that's really it for high-pass filters. I mean, it follows exactly the same trend as low-pass filters. Don't believe me? Look at the math. The formula to calculate the cutoff frequency for high-pass filters is 1 over 2 pi RC. The formula for second order, FC, equals 1 over 2 pi times the square root of R1, C1, R2, C2. It's exactly the same. Everything stays the same, even the design for the second order filters. You just take a high-pass filter and you tack on another high-pass filter. And there you have it. So that's high-pass filters. Now, the last filter we have to talk about is the bandpass filter, which is probably the weirdest of the three. A bandpass filter is a combination of the high-pass and low-pass filter. And I mean that quite literally. It starts with a high-pass filter. Then onto that you tack a low-pass filter. And there you go. C2, R2, R1, C1. And that's it. The curve for this looks like you took a high-pass and low-pass filter circuit and put them together, and that's pretty much what you see in the curve. You've got what starts out like a high-pass filter, and then on the other end what looks like a low-pass filter. And I drew that over the curve, but that's okay. And again, it's got the same behavior. Here's FL. FH. Here's FL. That's the high pass cutoff frequency and the low pass cutoff frequency. Now, that's really it. It's just two filters stuck together, and each side is solved individually. That's it. So you solve for the frequency you want for the high-pass filter, and then you solve for the frequency you want for the low-pass filter using the equation that is exactly the same for both. FC equals 1 over 2 pi RC. And then you know how to solve for the slope. I'm not going to write that equation again. You know it, and you know how to solve for what this gain is here. Each filter is treated individually. It's just going through the high-pass filter, and then that signal's passed through the low-pass filter, and then that's what you get out. In and out. Easy peasy. Now, there is one thing I should mention about bandpass filters is that there is a third frequency of interest, and it's right here in the center, called FR. It is the center of resonance frequency, and F of R is equivalent to the square root of FL times FH. But that's really the only other equation you've got to know. So, that is it for filters, or passive filters at least. High pass, low pass, and band pass filters. All the math, all the lovely, lovely math, all the drawings, and all the math. So, there you have it. If you have any suggestions for future videos, please leave them in the comments below. I'd love to hear them. But other than that, I'm humanHardDrive, and thanks for watching.